So the quantity, force times time, Ft, actually has a special name. It's known as the impulse. So the equation that we've just derived, Ft is equal to the change in momentum, actually has a special name. It's called the impulse momentum theorem, and it says that in order to change the momentum of a body, we need to have an impulse. So a corollary to this is that if there's no unbalanced forces acting on the system, then there can be no change in momentum. So in a minute we'll be looking at conservation of momentum, and this occurs when there is no impulse. But let's think about what impulse tells us about car crashes. During a car crash, we have a car which is travelling at some initial velocity, and then it comes to a stop relatively suddenly. So that change in momentum is fixed for that crash, as the change in momentum is the mass of the car, or if we're considering the momentum of the passengers, it's the mass of the passengers times the initial velocity. That is the change in momentum, as the car in a crash always ends up stopped. So in a crash, we want to decrease the force felt by the passengers. It's the force acting on the passengers that does all the damage in a crash. If there's no force acting on you, then there's no way that you can be hurt. So what car designers try and do is decrease that maximum force acting on the passengers. So the impulse-momentum relationship actually tells us how we can go about doing that. If we want to decrease the force on the passengers, then we need to increase the time over which the passengers come to a stop. So one way that cars do this is crumple zones. Let's have a look at a clip now showing crumple zones in action.
So you can see the crumple zone increases the time for the collision. Here it is again in slow motion. So this significantly decreases the maximum force on the driver. Now if we have a side-on collision, there's a lot less crumple zone, and so it's much more dangerous for the driver.
Now that you've seen the crumple zone in action, let's look at a couple of examples of using this impulse momentum theorem.
So the question is, a driver travelling at 80 kilometers per hour sees a red street light. It takes the 70 kilogram driver 3 seconds to stop the car. What is the average force experienced by the driver over this time interval? So to use this, we're going to use the relationship between the change in momentum and impulse. The impulse, Ft, is equal to the final momentum minus the initial momentum. That's just the change in momentum. And so this is equal to m times the final velocity minus the initial velocity. Now we know that the final velocity is 0 as the car comes to a rest. So what we're going to need to do is convert this initial velocity from kilometers per hour into meters per second. So the initial velocity is 80 times 1,000 meters, and then to get it from hours into seconds, we divide it by 60 times 60, and that tells, doing that on the calculator gives us 22.22 meters per second. And so now we can rearrange this equation here to get the force. So the force is equal to the mass times the initial velocity over the time, and we've got a negative sign there. This negative sign indicates that the force and the initial velocity are in the opposite direction. So this is equal to negative. The mass of the driver is 70 kilograms. So we've got 70 times the initial velocity, which is 22.22, and over this time, which is 3.0 seconds. So solving that, we end up with 518 newtons. And so we should just give this to two significant figures, as this data is all to two significant figures. So that's equal to 520 newtons to two significant figures. And we've gotten rid of the negative sign, so to account for that, we should say in the opposite direction to the initial velocity. Okay, let's solve another problem. So this question says, the graph shows the force acting on a 5.0 kilogram block over a 10-second time interval. At the start of the 10 seconds, the block is at rest. Calculate the speed of the block at the end of the 10 seconds. Here's the graph. You can see its shape. We've got force on the vertical axis in newtons, and on the horizontal axis we've got time in seconds. So to solve this problem, we're going to need to use that the impulse, the force times the time, is equal to the change in the momentum, which is equal to the mass times the final velocity minus the initial velocity. Now we know that the initial velocity is 0, as it tells us in the question that the body starts from rest. So now this is a bit tricky because we've been given a graph, but to work out force times time is just the area underneath the curve on the force times graph. So let's split this into three sections. We've got two triangles and a rectangle. You could just treat it as a trapezium if you want to. So force times time, and we'll go from 0 to 3 seconds, is just this area here of this triangle. So the area of a triangle is half the base times the height. So we've got half. Now the base in this case is the 3 seconds, and the height, this goes up to 10 newtons, so that's 10. And then we can work out the force times the time going from 3 to 6 seconds. In this case, we've got this rectangle here. So a rectangle is just the base times the height. So the base is going from 3 to 6. So this length here is 3 and the height is 10. So that is equal to 30. When we do this one, we end up with 15. And force times time going from 6 to 10 seconds. Once again, we've got a triangle over here. And so that's half the base. The base, we're going from 6 to 10. So that's 4 seconds. So 4 times the height, and the height is 10 newtons. So that is equal to 20. And all these have units newton seconds. So this tells us that the force times time is equal to 15 plus 30 plus 20. So that is equal to 65 newton seconds. And that is equal to the mass times the final velocity. And so the final velocity is equal to 65 over 5, which is equal to 13 meters per second. Now, if this force continued and went below the axis, that would actually be a negative force, and if that was ever to happen, we would need to subtract the area underneath the curve from the area on top of the curve. So if we had any area underneath the curve here, that would actually act, that would be a force acting in the opposite direction to the motion of the object, and so would be a force slowing the object down.